Dear all, as we all know that the Alzheimer's disease is a program assessed by the NRAA research framework. Biomarkers for Alzheimer's disease are grouped into those A beta, tau, or neurodegenerations. That means the ATN criteria. But for most countries worldwide, the PET and CSF are not easy to be achieved. Meanwhile, the MRI has become very popular in different hospitals. So it will be great if we can identify robust imaging biomarkers based on this non-invasive technique. We all know that we can get a different modality of brain imaging, such as structural MRI, differential MRI, function MRI. So if we want to get more detailed information searching biomarkers for Alzheimer's disease, we need hard work on developing imaging analysis of these measures. And that means we need more artificial intelligence network. In fact, we can get different information or different features from this imaging, such as the brain activity, brain network, the volume, the granular volume, the methods on white matter fibers. We can learn the impaired mechanism, the early diagnosis, the personal prediction with these features. If we can extend these frameworks from one side to multi-site, we will get robust features for early individual prediction of Alzheimer's disease. There are three primary features characterizing a biomarker. 1. Objective and qualitative. 2. Reproducible and generalizable. 3. Neuroscientifically interpretable. However, we have performed many group comparisons based on the data from one single site. Here, I do not mean that this kind of analysis are not important. However, I want to argue that we should pay more attention to independent cross-validation and individual prediction with the machine learning method. For Alzheimer's disease imaging biomarkers, we can investigate the producible qualitative features from the local brain regions, the whole brain, and the brain networks. Many excellent studies have been published in the past years. Convergence evidence shows that we can get good models from these skills. I will give some examples based on our latest work in the following. Remember, one cannot make bricks without stone. That means we cannot get any features if we do not have good data. Hence, all the following examples work on an in-house dataset and a public identity data with around more than 3,000 subjects. The Alzheimer's disease is known to target hippocampus regions. Therefore, the first example is about the hippocampus radiomics features in Alzheimer's disease. The hippocampus undergoes macrostructure changes before severe atrophy, and pathological changes such as neurofibrillary tangles or A beta are not directly detectable at the current resolution of the clinical MRI. Thus, novel MRI analysis that yield more incredible information about the changes in hippocampus would be a significant contribution to the Alzheimer's disease. The radiomics features, a method for text analysis, provide more information about the first, second, and high-order morphological features for Alzheimer's disease. So, the radiomics features provide increased precision in diagnosis, assessment prognosis, and prediction of therapy response of the Alzheimer's disease. The first aim of this study is to explore whether the hippocampus radiomic features with a reproducible change pattern can serve MRI imaging markers for AD using multi-site MRI. Here, there are around more than 700 subjects from 6 sites in China, and we also include an independent dataset from Italy with more than 1,000 subjects were included to further assess the reproducibility and generalization of these findings. The second hypothesis is that these radiomic features or classification output have a solid neurobiological basis, thereby showing preliminary promise as a potential marker of Alzheimer's disease. For this purpose, we investigate the neurobiological basis of the hippocampus radiomic features by relating these features to other variables, including the MMSE, ApoE, CSF A beta, tau, and also the progression of the disease status of the high-risk subject. That means the mild cognitive impairment subject. Hippocampus radiomic features different among the Alzheimer's disease, mild cognitive impairment, and normal controls. Notably, this result showed that the difference map was significantly related between the Alzheimer's disease, between the adenine and the enhanced database, which validated the reproducible of the radiomic features. Secondly, the cross-validation analysis suggests that the hippocampus radiomic features can serve as a robust biomarker for Alzheimer's disease. Thirdly, we can get that for the high-risk subject with more than 5 times visit, the changes in different radiomic features had a high uniform variation trend with the change of the cognitive ability in the progress mild cognitive impairment subject. And we all know that in the Alzheimer's disease subject, the atrophy had been shown to start in the medial temporal lobe and then spread to the posterior temporal lobe, parietal lobe, and then eventually to the frontal lobes. It will be great if we can evaluate which region provide a key contribution to the imaging by. These days, the deep learning models make artificial intelligence more popular in Alzheimer's disease prediction. Traditionally, we input imaging features in, and with the predictions go out. There exists a black box for this framework. However, as doctors or patients, we all hope that we can open the black box and know the exact cause of the Alzheimer's disease. In another work 2 years ago, we developed a 3D attention network that can not only capture imaging biomarkers with attention mechanism and can advance the diagnosis of Alzheimer's disease based on structural imaging from cross-validation, important reason, and neurobiological basis. The producibility will evaluate user cross-validation on in-house data and the public adenine data with accuracy around 87%. And more importantly, the effectiveness of the 3D attention model was further validated by its good performance in predicting the mild cognitive impairment subject who progressed to the Alzheimer's disease with 3 years with accuracy around 71%. Significant association between the classification output and clinical characters of Alzheimer's disease provide solid neurobiological support for the 3D attention network model. And in a short summary, our finding highlighted the potential for structural brain imaging to provide a serialized and neurobiological interpretable imaging biomarkers for Alzheimer's disease. And we all know the Alzheimer's disease is associated with disruption in brain activity and brain connectivity, which suggests that the Alzheimer's disease may be a disconnection syndrome. Follow a complex analysis steps, we found that relative to the normal controls, Alzheimer's disease subject was associated with the significant reduction in functional connectivity and local activity in deformal network and cingulate gyrus, and also along with the increased connectivity or local activity in the prefrontal lobe. Leave ones out cross-validation established that diagnosis status and the clinical scores could be predicted with high accuracy. And collectively, our finding highlighted the potential for a reproducible functional brain imaging biomarkers to aid the early diagnosis of the Alzheimer's disease. More importantly, we found that with these impaired connectivities, we can cluster the Alzheimer's disease subject into 4 subgroups using a non-negative matrix fraction method. And we also found that this difference in connectivity and the difference between the Alzheimer's disease subtype was found in cognition, structure methods, and cognitive decline patterns This comprehensive result offers new insight that may advance precision medicine for Alzheimer's disease. These findings show that the brain imaging features can provide believable and robust information to discriminate the progress of Alzheimer's disease. And also the classification analysis result provide encouraging evidence for us for using the brain imaging feature as a potential biomarker for clinical application in Alzheimer's disease. Also, the change brain imaging features was strongly associated with its neurobiological basis. For imaging biomarkers of Alzheimer's disease, we still have a lot of work to do. Firstly, many researchers have realized that the reproducibility is one of the keys for imaging biomarkers of Alzheimer's disease. And now they start to call for more groups and countries to work together to provide a real cross-validation for certain biomarkers of Alzheimer's disease. We should admit that most of the previous studies, the data are carefully controlled for different variants. However, if we want to put the lab research model to a real clinical application, we need to validate these models with real clinical data. We have made all the toolkit open on my GitHub. Please do not hesitate to contact me if you have any questions. And here, we want to argue that if you have any good idea, good data or code for Alzheimer's disease imaging biomarkers, you are welcome to join us to study on our data. Lastly, I want to say thanks to all my collaborators, and thanks to all the fundings, and also thanks for the chairs. Thank you for your attention. You can follow me on the following posters, Google Scholars, and Twitter. Thank you. Thank you again.